All right, welcome everyone to Professor Claudio Silva's talk. So it's my great pleasure to honor to introduce him. Claudio is an institute professor at New York University, jointly appointed in the Center for Data Science and the Tandon School of Engineering. He's also affiliated with the Center for Urban Science and Progress and the current Institute of Mathematical Sciences. His research interests include visualization, visual analytics, machine learning, reproducibility and provenance, geometric computing, and computer graphics. And he received his PhD at the University of New York at Stony Brook in 1996. And he's advised 20 plus PhD students and mentored 20 plus postdoctoral associates, and has over 300 publications. So he has a lot of awards, but just to read the first few, he was elected chair of the IEEE Technical Committee on Visualization and Computer Graphics, and is a fellow of the IEEE and received the IEEE Visualization Technical Achievement Award. And so today he's going to talk about data-driven cities and accessibility, which is a very interesting topic. So looking forward to your talk.
Thank you, Stephen, and thanks everyone. It's a real pleasure to be here. It's I mean, the issue with students and publications has all to do with the fact that I'm old, but I'm actually this work that I've been talking about. This has been work, as you guys are going to learn, that I've been pursuing for the last 10 years, pretty much since I got to NYU. And as you can see here from the huge number of people that actually have worked with me on this, this is definitely a very joint work with a number of extremely capable people. So let's go through this here. Let's see if I can get my okay. So what I'm gonna mostly talk about today is I'm gonna talk about data-driven cities, right? About the process of big data in the context of urbanization. I'll give you actually the context of the Center for Urban Science and Progress and how I got involved in this, because I'm really like a computer scientist. So how does a computer scientist gets involved in this kind of thing? I think it's kind of an interesting story. And then I will show you like a sample of these urban data science projects that we've done. In particular, I'm going to focus on scenery imagery for improving accessibility. And then at the very end, I'll give you some reflections and kind of like moving forward as we are doing this. So just to give a context for the kind of work that I do, though, my group does a few other things than urban science. So I joined NYU in 2011, and one of the things that actually I didn't anticipate was I got involved in a number of like different kinds of projects. So one of them, for instance, was I helped the Major League of Baseball to develop the StatCast. I know that Korea is a baseball country, okay? And so it for me as a Brazilian that knew nothing about baseball, it was really interesting that that actually I worked with the Major League of Baseball on developing technology for baseball tracking. So I find it really very interesting. So this thing, this image that you see on the back there was on Vice Sports. That image was actually from one of our prototypes, and that's why you see kind of like all the noisy speed velocity plots there on the back. That was never supposed to see the day of light. That was just kind of like a debugging tool. So from that, we actually started, this kind of grew into a research area in my group. We've been building some hardware. We have this thing called the Lego tracker that is actually some intelligent hardware to track players, and we are now in the third generation of this. Actually, this was second generation, and we kind of like expanded. I've been doing work on sports analytics, like how do you compute win probability for like esports, right? For like CS:GO and things like that. Fundamentally, my area is really visualization and graphics. We still very active on this. just some examples here. That was a KAI 2020 paper on kind of like interactive techniques for straightening skeletons. We have been developing this tool called Open Space with the American Museum of Natural History, Linköping University, and the University of Utah. And we've been developing NLI interfaces for visualization systems. So just to give you a context that there's other things going on in the lab. But what I would really focus on for the next 45 minutes or so is urban computing. So we've been really deeply involved in urban computing. As you're going to see, actually, urban computing, there's going to be a lot of visualization and graphics, but a few other things, because it's fundamentally a very applied area. So this started for me actually with this thing called the Applied Sciences New York City Initiative. So what happened is that New York, when I got to New York City, the city was just trying to get out of the financial crisis of 2008, and there was this really big investment that Mayor Bloomberg wanted to encourage New York City-based entities, in particular universities, to invest more in engineering, right? So it really wanted engineering and applied sciences, and actually KAIST was kind of like NYU's response to this call from the mayor, and I'll tell you what we got out of that. And the real big thing here was that a bunch of smart people realized that the world was fast urbanizing, right? And then one of the things here, in particular, we're in the process actually of building a whole bunch of cities now that is going to be kind of like something that we are never going to see again in the century. We're going to see the building a number of cities until like 2050, and then we're going to kind of like plateau, okay? And we're going to, one of the things we're going to see is that 90% of the population in the world is going to be living in cities. So there's like this whole need for developing new technologies for cities, how to make them, better, more livable, right? More fair. So that was the context that KAIST was created. And at the time, what the mayor was giving to NYU was this thing on the right. I mean, now it's a real thing, but it's actually this big building in New York. What actually is a big, like in New York, real estate is really valuable, right? So this was the idea here was, okay, we're going to give you this, and you guys have to deliver on producing more engineers, right? And NYU did this. Actually, Columbia did another version of this, and then there's Cornell Tech that is even a bigger version of these things. And that's why, like 10 years later, if you go to New York now, you're going to see much more engineering in New York than you did that was 10 years ago. So this was a big decision that government made. Okay, so and one of the reasons that Bloomberg had to invest in this, okay, is his belief that data could make a difference. And I'll give you one example of this here. And this is work that the mayor's office had done, not us, right? So the mayor's office had created this office of the director of analytics. And in one thing is they have like these things called like city inspections for different things. Like, for instance, there's this thing called illegal conversions. I don't know how many people have heard of what an illegal conversion is. It's a technical term. It's like this. Imagine that someone is living, someone is using a dwelling, a home, or some kind of building for something that is not supposed to be used for, okay? So let's say that a certain, apartment is rated for 3 people to live there, but you really have like 15 people living in that area, okay? Right, so for whatever reason, it's so that is an illegal conversion, okay? And what happens that New York City has a very small number of inspectors for these things, and the hit rate of the inspectors. So before the Office of Analytics was doing the work, they said like, okay, right, how do we find these things? They, the inspectors would have all this leeway to decide where they would go to do the inspections. So this guy, Michael Flowers, that actually was one of the advisors for KAIST for a while, he changed the way that they did this. He took a bunch of databases, and that's actually this thing here on the bottom here. He took a bunch of databases from this city, and by actually just putting them together, he developed a relatively straightforward system for doing predictions of what would likely be real illegal conversions. Okay, and then the hit rate on the actual visits went from something like 13%, okay, to something like, I think was like 90%, okay? So it just showed that just by using data, you could make much more effective use of city resources, right? And this was kind of like the idea of kind of like this entity for KAIST. So when we started this, right, there was kind of like this vision. So what do we want KAIST to be, okay? So it was, imagine that the city is this thing that has infrastructure, has the environment, has people, okay? And we wanted to put all this data together, okay? And then, I mean, the data actually kind of like would come on. And then we wanted to add computing to this and try to make better use of that data, right? So it was like this really, kind of like, how do we do this? And one of the challenges that we had in trying to do this, in particular for computer scientists, and I assume that most of the audience here is some version of computer scientists, is that, of course, you can always help the city in one way or another, but the issue is, how does it help you back, right? So let's say you're a PhD student working on this, are you going to be able to get like good papers out of this? Are you going to be able to apply for the best postdocs, right? Work, get the jobs at the right companies. So I think that it was with this in mind that we had to imagine how to set up this research program. So I will show you some examples of this. So probably one of the best examples of a project that we envisioned at that time, and this was very, very early on in the history of KAIST, was the Sounds of New York City project. Okay? And I'll talk a little bit about this so that we can, So this project took us, if you see here, it took us a few years to start, right? So KAIST started at 2012. We talked to the city. We talked about a lot of different potential projects. We started writing proposals to the different agencies. Eventually, we get $5 million from the National Science Foundation to do this. Okay, and as I'll actually show you like a piece of a video that we produced for the vision for this project very early on. So let me show you that. Now, this has sound. Let's hope that the sound is high enough that you guys can hear.
There's a noise coming from the traffic or the garbage truck. I think to be really affected by sirens here.
It makes it harder to kind of focus because there is just so much background noise to block out.
Noise pollution is really one of the topmost quality of life issues in the United States. More specifically, in New York City, it's been estimated that 9 out of every 10 people, 9 out of 10, are exposed to harmful levels of noise. To address the issue of noise in New York City and in urban environments in general, we're proposing the SONIC project, Sounds of New York City. The idea is to construct a novel cyber-physical system, which includes a hybrid distributed network of sensors and citizens for large-scale noise reporting. In this network, citizens are empowered by apps that help them connect to the city and with each other in an effective and responsive manner, while sensors make use of cutting-edge machine listening methods to constantly provide a rich description of their acoustic environment. Information from the network flows through a cyber infrastructure that analyzes, retrieves, and visualizes data to facilitate the identification of important patterns of noise pollution. It's intended for decision makers at city agencies to strategically deploy the human resources at their disposal to act on the physical world.
We're in the Cooper Union Anechoic Chamber in Manhattan, New York City. The reason we're in here is this is where I carry out all of the acoustic testing, mainly on the project's MEMS microphone that we use that allows us to produce accurate acoustic data at a very low price. It's around $10 for this device here. I test this microphone in the anechoic chamber to make sure it's able to produce accurate data that is up to the standards required by the city agencies such as the DEP, the Department of Environmental Protection. We use a single board computer called an Odroid. Now, this is going to carry out all of our processing on our data in situ within our sensor itself. So our sensor costs around $100 in parts, which is very low cost compared to other solutions. And this has a potential to be scalable and be deployed across the city in large numbers.
Being able to measure decibel levels is a crucial first step for noise monitoring, and that allows us to say where noise is happening and when, but it doesn't allow us to answer the question why. So in order to address that, our sensors have to be able not only to measure the loudness of the sound, but also to be able to automatically identify different types of sounds. So I'm going to show you a demo of the machine listening algorithm that we've been working on. The algorithm is based on deep learning or deep neural networks, which is the same artificial intelligence technology that's already revolutionized fields like image recognition and automatic translation. So here you can see the algorithm listening to the environment, analyzing it in real time, and displaying how confident it is in recognizing the sound that it's hearing. To see how this works, we're playing it sounds that it's never heard before, and we can see how the algorithm reacts to these sounds. For our first prototype, we're focusing on the sounds that New Yorkers.
So one thing I want to point out is that this was about 10 years ago. Okay. So that's why it looks dated, but it should look dated, right? In that this was like 10 years ago when we were putting all this stuff together. And there was all kinds of stuff that we did on this. Like we had to build our sensors. We had to build the software for our sensor network. So Ichak actually helped with the sensor network. Ichak was my postdoc at the time that came from Yale. And I mean, we had to build everything ourselves, okay? And I mean, but this actually worked really well. By the end of the project, we had an industrial type of sensor that actually, we could, people that were complaining, so the city was using this for a while, the Department of Environmental Protection, that people that would have noise complaints, we could ship them one of these. This was actually designed so that they could install it themselves, and it would automatically connect to the network, to our sensor network, right? They had an app that they could actually then use, I mean, so there were all kinds of, we developed analytics tools that allow people to actually, study the different sounds that they were getting. This project led to, I think, probably hundreds of publications, and it affected a lot of students. So I think that this is just one of the examples of where like we started, right? And I'll go back to another one, but and then I'm going to jump forward to much closer to now what we've been doing at KAIST, but really trying to push forward not only on kind of like the application in the sense of like the urban work, but really trying to make sure that you're pushing forward on the computing. So, for instance, Justin Solomon, that now works for Adobe, got like a Best Paper Award, actually probably multiple Best Paper Awards for work that he did on this project. Some of his papers have thousands of citations now. So I think that we are very lucky of trying to start in this domain very early. But also, I think that it did require a lot of thought to actually try to frame the problems in such a way that they would have this impact. For instance, this is very recent. And you can recognize Charlie here on the right. He was the microphone person, okay? So Charlie now has been working on a completely different sensing network. This one is for flood. It's called FloodNet. Actually, New York City is funding this to the tune of several $1 million. The idea here is to develop these flood sensors that can find very, very local floods. So because there's some areas that is just that the flooding that happens is not like the kind of flooding that you get like when the ocean just comes and invades on let's say a beach, right? It literally, there's some kind of event, and then it might flood, a few meters of a street, right? And you want to be able to measure this, and they've been developing these sensors now, and he's working with Elizabeth Hanath and Andrea Silverman on this together with people from the city. So one of the things that is interesting is that I believe that some of this technology is going to be deployed throughout the world as it's being developed, mostly to be very, very inexpensive, right? To allow people to just replicate this. It's the same with the sensors that we did for Sonic. Okay, so before moving forward to now, I want to tell you about another project that when we started KAIST was really also very important. It's very interesting to always have like data sets that one can use as a way to try out different algorithms. Like, for instance, in the back days of scalable graphics, I see Professor Yoon there. It was like the Boeing 777 data set, right, that we would be using, or the power plant. The taxi data was that data. I mean, in a way, it still is the data. So what happened is this, right? So New York City tracks every single taxi, right? It tracks every single taxi. Every single taxi trip is tracked, right? And I discovered this, I don't remember exactly when, and the data was not public at the time, but I was able to talk to the commissioner and start getting copies of this. At that point, this data was useless, right? So what I mean by this is that they had this data, and I would tell them like, hey, can you give me the data? And then they gave me a spreadsheet, and I'm like, hey, a spreadsheet for one day. It was 500,000 trips, okay? And I said, no, I need this for a year. And they're like, what you're gonna do with this? It's useless. How are you gonna handle hundreds of millions of trips? Okay, they had never heard of like database technology, right? Okay, but it's amazing. The interesting thing about such a data set, and actually I'll show you examples of this kind of data, is that you can learn all kinds of stuff from this kind of data. So these are two plots. This is actually all the taxi trips, just the amount for 2 years in a row. So you have 2011 and 2012, okay? And this is just the weekly, ups and downs of taxi trips in New York aggregated, right? From this, you can notice things like, look at this, like what are these red peaks down here, okay? So most of these, you can actually just, if you Google these dates, you're gonna find them like that. These represent, usually it's gonna be hurricanes, it's gonna be, in one of the cases here is, I think that there was a strike of the cab drivers, okay? But you can see things like this. Look, this here is summertime, look. And then going back to classes right here, right, okay? This is Thanksgiving. Actually, one of the things that is very hard for you guys to see is right here, there's like a little tick, okay? And if you're not really very attuned to this kind of stuff in the US, you're not going to notice, but that's Valentine's Day. On Valentine's Day, you see kind of like this, this little thing there, right? Okay. So you imagine if just like a 1D plot of this kind of sensor, right? This unsuspected sensor can give you that kind of information, right? Imagine now when you actually take the spatial component of this, okay, right? It gives you all this extra data. Right. So for instance, I'll give you an example here. This here is just 2 hours on a Sunday. Okay. You see 6th Avenue kind of like with no taxis. Like what happened here? Okay. This is actually the bike tour. Like every beginning of May, you have this citywide bike tour that they close these streets. Okay. But the thing is this, if you take this data set, so you take the 105 million trips a year where you have location and time for each one of these trips, and you actually have other attributes. One of the things that we've been able to demonstrate with our research, and this is distributed on tens of papers, some of them at SIGMOD, some of them at Viz, at other venues, right? is that, you can really figure out a lot of what is happening in the city, right? From these kinds of, like, if given enough sensing, you can do this. So what kind of research was generated? Right? So, I mean, one of the first papers we did was this thing called this, it was we call it taxi viz, okay? So, but calling it just like a viz tool is kind of a little bit of a simplification of this. Like, we had to develop, for this first one, we have to develop our own specialized database engine, the rendering engine, the plotting engine, the query language. There's so many components to this that we had to develop to make this useful. And one of the things that was really cool is that this generated a whole sequence of very interesting papers that people could use. And at the same time, right, when we shown this to the city, and this comes from the office of the limo and from the Taxi and Limousine Commission, they're like, we're truly blown away. We couldn't see that we could use our data this way. They bought Macs because our first version only ran on a Mac to actually use our software, right? So I think that this is the kind of project that when we created KAIST, we really wanted to do, is like to create whole areas of research for computer science students, right? That would actually then be able to feed back into the urban domain, right? But that actually would generate new CS research. So I'll give you, there's a bunch of these. I'm not going to have time to cover them. But, it goes all the way from completing information that you don't know. This is one day of a taxi, of the trips of one taxi in New York City. You're going to see like one taxi covers a substantial part of the city, just like in the course of one day. I'll keep going. Otherwise, I'm not going to make it through the rest of my talk. This is an example. I just have this one slide on the database. If you see here, we actually tried a bunch of things. Commercial databases for this, right? Okay. And compared to what the performance of our system was, we were orders of magnitude faster, right? Had nothing to do with, this was the work of my database colleagues into this. This is Harish, he's now at Microsoft Research India in the database group there. There's like, to be able to do data mining on such a big collection of data, right? We also developed a bunch of techniques for this. These are actually based on computational topology. I'm not going to have time to describe them. But one of the things that is kind of cool, right, is that I demonstrated to you that there was that example of the bike city tour. What we could actually do is that for the kinds of algorithms, we could say, oh, we found this feature interesting. And then what the system would do is that it would show you all these other disruptions in the system that were similar. For instance, if we look at the bike tour, then it was similar to the Dominican Day Parade, right? And to the Gaza Solidarity protest, right? So it's really interesting. Once you have the data, okay, and you have these, and you have like tools that is actually able to find these things, you can do all kinds of, you can learn all kinds of things about how the city behaves, right? But you do need to have these scalable tools and develop these scalable tools. I'll jump over a couple of these. The first 3 or 4 years were like super fun. Everything was really super novel. Lots of like it was. I think that it was kind of like a child in a candy store, right? Lots of these things. And one of the things that I want to point out is that, in a way, a lot of the techniques that we are using, they are things that you might be doing for computer graphics. Like, for instance, if you're trying to create quadrangulations, right? Okay. So this would be a geometry processing, effectively it's geometry processing, right? Or actually a lot of the same techniques, even though these are less used in this domain, some of these computational topology techniques are not as used in machine learning, but I think that their use is going to increase, in order to try to understand models there. So the arsenal of computer science that we've been developing for 50 years, turns out to be very useful here. You have to, you need to do modifications to make them work in this domain. I'll have this 3-second segment on cities are not 2D, and then I'll go to images and accessibility in a sec. But one of the things we realized also very early on is that GIS systems did not really work for us very well, okay, in cities like New York, because a lot of times we have a situation that cities are not, 2D, okay, and some of the operations that when we were working with urban planners, people are interested to, like, let's say that they were interested to try to understand what is going to happen to a neighborhood if I allow a certain build to be built, okay? They wanted to understand, for instance, how it would affect the views from other buildings, okay? You cannot do this very easily by just having 2D representations for cities, okay? And we spent a lot of time then building systems like Urbane for doing this kind of stuff, and to help architects with designing buildings. This was at SIGGRAPH Asia. You have things like this is actually really interesting. This is just changing the building topology, the building typology, so as to maximize the quality of views from that building. Okay, and we worked with urban planners on this. So there was like a whole set of these applications that we were working with people. And more recently, one of the things that we got very interested in is the issue of accessibility. So what's the issue here, right? We actually started to notice this actually as part of, after we built the 3D component of the city. One of the things that I started noticing was that, for instance, like how to navigate the city. Sometimes, you're in the winter, there is a certain sidewalk that you cannot pass because there is snow that just kind of like accumulates there, right? So I remember when I had small children, if I was carrying like a stroller, I couldn't get across. Okay. Other times during summertime, it would get too hot, right? If you're directly in sunlight, that thing, and then start thinking, like, does this affect people that have, that maybe they're using a wheelchair, maybe they don't have, they're not able to easily move in between sidewalks up and down, right? And we started actually trying to figure out how can we quantify those things, and I'll show you some of these things in a sec. But another issue of this, and these are images from J.R. Rizzo. He's a professor at NYU. So JR, and I don't know if you guys have this issue in Korea, but this is very New York. So JR started to accumulate these images of all these hazards for people, in particular for visually impaired people. So JR is legally blind, and you have things like this. You have these potholes, right? That are really dangerous. You have these situations here, like these uneven sidewalks where this thing is just totally someone would trip on this. I'm only showing like a really subset of the pictures he has. Like New York has a terrible way to collect trash. I don't know if you guys, anyone here that has visited New York remembers. They just put the trash on the sidewalk. Sometimes like it accumulates. I mean, it's actually quite a lot, right? For most of us walking on the sidewalk, we never notice how dangerous that can be. But it can be truly dangerous to people that cannot see those areas, right? I mean, actually, so one of the things that we are trying to do, the same way that, so we started projects to make it easy to do sensor networks on cities in the context of Sonic, and then you saw how it's getting reused in FloodNet. We started, trying to understand sidewalks and the pedestrian infrastructure better. Okay, so I mean, the first thing, what's the first thing that you need when you do this, right? Okay, so we need to know what the sidewalks are, right? We need to know what materials they are. We need to know what shading information they have, how much, what is the physical environment that actually, how these sidewalks, receive light, right? So we've kind of like been doing this kind of like systematically, right? So one of the first things we did is we've been developing these techniques for actually kind of like computing shadows in the city. But notice that these are not just shadows like in a game. These are accumulated shadows. So what you're seeing here, let's say that you look at this picture here in Chicago here. What this thing here is the amount of light that got accumulated in this area on a particular day. Okay, so this actually gives me a notion of the thermal index of this. Okay, and so we developed really efficient techniques for this. It was very interesting, actually. You can see a real use of this. This is it was a New York Times article on this data. Okay, so effectively we figured out that, okay, if we have the model of a city, now we can very efficiently start to computing these data, right? Okay. One of the problems is that there is a lack of data on the city. For instance, Marian Husseini, that was my PhD student, and she did a survey of 178 municipalities across the U.S. So only 20% of them you actually have sidewalk data. Okay, only 11% of them you have crosswalk data. In only 8% of them, you have material sidewalk data. Okay, so the amount, there's a humongous amount of data that doesn't exist that we need. Okay, right? We started, actually, Marian, in her PhD, she started addressing these things. So Marian finished her PhD. She's now at MIT at the city Form Lab with Andres Setsuk. But so give you an example of the work she did. So she tried to compute surface materials, right? And the reason for doing this is not because we just like surface materials, is the fact that they affect the risk of outdoor falls, right? They affect the accessibility for wheelchair users. This paper was published last year. I'm just gonna just quickly tell you. So she started with the notion that she wanted to classify sidewalks among these 8 materials, right? And she wanted to be able to segment them and actually know what the material is. This doesn't exist for New York, obviously. So she was really lucky. She looked, and Boston had data. Okay, so actually, what she did is kind of like this hot pot of a technique in a way. This was very laborious. She took the Boston data. She trained a machine learning model that is able to find the different materials. Okay, but it actually could not determine all the materials very well. It could actually determine all the materials that she needed. So she effectively had to fine tune and use active learning for actually adding the new materials. But the result of her work in the end was a really nice model that, I wouldn't call it like industrial strength, but it's really, really pretty good. Okay, so you can now apply this to effectively, at least most US cities, and it would provide you with a good set of materials. One of the things that is really cool here is when you actually start to merge data. So together with Fabio Miranda, that was one of my PhD students, he's now a prof at Illinois, they took the shadows data with the materials data, and then they worked on computing a risk of fall per sidewalk data set, okay? Right, so this can help people determine when you can actually walk on a sidewalk, right? And how likely, someone is to fall there, right? So I think that this is the kind of work that, of course, like these things are going to require a lot of more work, but that I find really super exciting about. Another thing that she did, and I only have one slide on this. This paper was just published about a couple of months ago in the Code. So sidewalks, there is barely any sidewalk data out there, right? So we have very good road networks, but we don't have sidewalk networks, right? And now we just released an actual system that people can just compute this for pretty much any city you want. I don't know how well they would work in cities in Korea. Maybe you guys have much less problems with these sidewalks, but it would be kind of like interesting to try to see this. But for U.S. cities, this has been been like a game changer for us in terms of moving forward with this kind of research. Okay, so I have one more thing that I want to tell you is, so I told you about this taxi data. What is it? Was point data. I know that the taxi is here, so something happened, and it went there later, and we knew. So this kind of thing let us do things like to know when the road network was being used, when it was not being used. It allows us to allow some people in the economics department at NYU, one of them that is not professor at MIT, do work on economic models on the taxi drivers, okay, because there's also like price and tipping account. But I would say that the thing that those models only effectively they're just like relational data with time, right? So you have kind of but then this data set kind of like showed up in our hand a few years back, where a company in Brooklyn put cameras on top of fleet cars and just let those fleet cars take pictures as it went along. Okay, so imagine this, right? So now you have a data set where you just have images. Imagine that you have a number of cars with images on top, and you just keep taking pictures. How can you use this? Okay, so in a way, this is a superset of the taxi data, right? It's not as extensive, but it's a superset. So you can see like there on top the kinds of images that this has, like because they had a camera on front and one on the sides, okay, right? And so we actually developed a system. Again, this is another thing. The person, you have 40 million images, okay? So someone dumps 40 million images on you. These images have been taken along cars taking random drives, where you don't control where they are. You just have those images, okay? So you now you need to develop a query system for that. You need to be able to visualize these images and to take and to be able to get meaningful and to be able to get meaningful information from them. So just some of the kind of stuff that we did. So one of them is this was one of the first pieces of work we did, was trying to extract pedestrian counts from the images. So we try to analyze collection of images in a neighborhood and try to just create pedestrian counts for the people, right? So we actually would take such a system and use this together with an age-based system for how people are walking to estimate pedestrian counts, okay? We also designed this whole query system where you could, and the reason for this is going to become obvious in a sec, where you can mark regions in your images, and you can say, can you find things like this, right? In order to do this, actually, what we did is that we took a VGG net, and then we got out of the final layer and just use the previous layer as a feature vector. And then we use LSH, to match things that are similar. And then you get something that actually works really well. You can effectively, you can do very fast querying, right? And then this allows you to do things like, okay, I like this facade. Where is there like another facade like this in New York? And I apologize for the fact that you guys cannot see this, but you do this query and then it actually would tell you where all this stuff is. That's what this thing is on the background here. And then if you actually were to click on any one of these, then it brings up the other stuff. So you can keep doing this, right? And what this allows you to do are things like, how does it connect back to accessibility? So you can do things like this. So streets are supposed to have this thing here, right? Okay. You can click for it and you can see the streets that don't have it, okay? You can find things like this. Look at this. This is a puddle, right? This is very dangerous here, okay? You can mark these regions and then you can query for them, okay? Right? So one of the things that is amazing also, from this kind of opportunistic sense, that's what I call this, right? Is that, because, these random sensors, by just driving around and taking images, they see the same place over and over and over again, right? You can actually have a notion of what was happening in time. So you can see when that corner was actually compliant to law and when it was not compliant to law, right? Okay. I didn't tell you about the counting stuff, but like in New York, do you know how they figured out how many people are on the street? So the Department of Transportation sends people. Someone stays there. They have a counter. They count by hand, and then what they do is that they would record that date on a spreadsheet, and I mean, I know that this is probably more accurate than what we can do by looking at images, right? But you can imagine that you can only do that for such a sparse sample that it's not really, and it's the same here. Like, I mean, of course, people can check, right? And they do check some of these things, but automating these kinds of checks. So all the things that we can do by that can be done by automating, right? So computing, being able to find the materials on the sidewalks, computing what the sidewalks networks are, being able to use computer vision for actually determining where potential dangers are or not. We can then see where in one of these, I think it shows where snow is accumulating, okay, and then you can merge that with the sun with the shadow data, right, to understand how fast you're actually getting the snow to melt. Okay, so all these things you can start to see that you can start to build models out of these things that you couldn't do, right, by any other means in an economic fashion. Okay, so I'll give you one more example here. Okay, so this is actually a collaboration with Chan Feng and JR that I already mentioned, and this is the first data set for visual place recognition. Okay, we had to do a number of things to actually be able to release this. One of the problems was actually we had to anonymize the data, right? But the idea here is for those that don't know VPR, the idea in VPR is you want to be able to show a region, and then you want to be able to find where this thing was taken, right? Without actually having the let long. One of the things that was kind of cool in this case is because we had the ground truth, you can throw it out, and then you can actually use this as a benchmark for these algorithms, right? Yeah, so we've had fun with this kind of data, okay? You can do things like looking at construction evolution, okay? So you can, one of the things, the city releases a record of construction and construction permits. This is public, right? But you actually don't know when the construction really started or not, right? Because there's a window of time that thing is happening, okay? So the cool thing is now you can take the stream of images that are supposed to see that construction happening, and then you can inspect them, right? So you can actually then, get you know. So it's kind of cool, like you having these data sets, having things like the taxi data set, like the like and like this image data set allows you to go back and do all kinds of these analysis that if you have the right tools, right, that you couldn't otherwise do. And this actually brings us to the end of something that is really important is the tools. Okay, so when we started this 10 years ago, we almost didn't have any tools for this. Right now, we have a whole bunch of tools. So, for instance, you know, the database group led by Professor Freire has developed a whole bunch of tools for like doing data cleaning, all this kind of stuff, right? Okay. And then there's tools like OSMNX from Geoff Boeing from USC. There's a bunch of tools that I showed you that we've been developing in that we've been releasing, and they're like on our website. But one of the things that we're really missing is still in this is something to actually put all this together. Okay. So one of the things that we've been trying to do now is actually to build an end-to-end, okay, community based open source tool for urban computing. Okay, and the idea is to actually, you know, urban computing actually needs a slightly different, or actually more than slightly different set of tools than just regular GIS systems, because regular GIS systems, you know, are really like, you know, aimed at very flat situations and the countryside. So anyway, this is work in progress for us. I think I'm going to be working on this for the next 10 years. So in summary, okay, I gave you a little view of how I got into data science for cities. Okay, I think that this area is very exciting. I showed you just you know, bits of work on this. It's very easy to find these papers just because they're on our group's website, or you can look at Scholar. I think that there's lots of opportunities. So and we are doing, you know, this is an active area of research for us. I actually just wrote a proposal with the folks from MIT to do more work on the sidewalks. I mean, all of this stuff is actually pretty active. And if there is time, I'd like to take questions. So thank you so much for coming to my talk.
Thanks so much for the talk.
So thank you for your great talk. So you just opened up some new perspective of the data-driven research. So I know you have some background of geometry and also 3D scanning. So I noticed that you have a very high quality geometric data of the New York City. So I wonder how you guys can obtain such kind of 3D model of the geometry first.
That's a great question. So actually for those, what we did is that, I mean, we were working with some urban planners on this. So a lot of it is actually extrapolated from OpenStreetMap that is pretty reasonable in New York. And then for the bad pieces that OpenStreetMap would be bad, the architects hand built the models for us. So there is no clever 3D scanning yet. Okay. We do have I have a colleague at KAIST. She's actually, her name is Deborah Leffer. She has actually been flying. She hired an airplane to fly over and do a super high resolution scan. It's actually open source. This is probably the highest resolution scan of New York City that anyone has done. But it's definitely I think it's an area of research to be able to improve the quality of the models. I think that there's lots of different ways to do this, and also there is a need. Okay, there's a bunch of need, for instance, for people to buildings need to be the facade has to be inspected, right, at regular intervals. Right now, this thing is done manually. we really need to either have drones doing this or have another technique that maybe does some clever thing with images to be able to inspect the facade. So there's a lot of need. All I'm saying is that very little work done in that area. There's lots of need for more work. Yeah, thank you for the question. Yeah, yes, please.
The data sets that you have are really key, and I was wondering if the collaborated mental health researchers on how the structure of the city, for example, the shadow data, affects, for example, happiness level of people with their mental health, for example, during the coronavirus, when we were points, for example.
That's actually great. We have not actually talked to mental health people about this. We have talked to occupational therapists, but more in the context of falls, right? So the most on the issue of falls, because it seems to be something that affects the elderly population, right? We did talk to people, and then there is collaborations going on, right? But not in mental health. That's a very interesting. Even if actually anecdotally, I think one of the reasons that New York Times article was so popular is because people are very concerned about shadows, in particular in the winter, right? People are okay. I'll say that there's an anecdote because it's kind of interesting. So people have personally sent messages to me with like, this building is going up and it's gonna block light to this thing here. And in at least one instance, I got such a message, and then I forwarded it to my student and say, can you take a look at this? And the person was computing the shadow wrong. Okay. so maybe even like just putting a tool out there that people can actually like, oh, okay, this is what's going to happen here. But I mean, it's not like we would have the time to make these tools available to people. But yeah, I mean, shadows in cities, in particular in New York, is a big thing. Yes.
I have a
Yeah.
visual place recognition. Before giving my question to you, I would also thank you for your informative presentation. This is my question. What made you assume that the side view image represent the visual impairment person better than the typical concrete image?
No, I'm not saying that they no, I was just saying that we have three different types of images from the moving cars, right? These images were not acquired with any specific purpose related to accessibility. It just happened that the data set was acquired by a company that made them to us, made them accessible to us freely for research purposes, right? And we are just showing that we have used those images for research that has implications in accessibility. So one case is this new benchmark for VPR, right? That the idea here is to actually test the algorithms for finding where someone is, right, by taking a picture. So I'm no way saying, and I understand that there is lots of different levels of visual impairment. Some of them are peripheral, some of them are from front. I mean, so I've talked to JR about this. Yeah.
My question was based on the abstract before the seminar. The abstract told me the side image represents the visual image.
then it's a mistake. I'm sorry. I apologize for if I'll read the abstract again. Yeah, thank you.
I have a question. So from what I saw, your sensor data seems to produce very high resolution information across the entire city. So how densely are the sensors placed within like the city to get like it seems like the sensors could track like the whole city, but I'm assuming you don't have it every few meters, right? Like how
I displayed lots of different, so there was at least 2 different ones like this. There was the taxi data set,
Yeah.
and there was the Carmera data set. So which one do you want to know? What
for example the noise data set that I
the noise data set is extremely sparse. Okay.
then how do you track the noise level from the entire city with sparse location?
No, we can't. So actually, so for the noise, and we are talking about this during, I mean, I don't know if it was during lunch or with I think maybe it was in the previous meeting. We put out, I think we put out just tens of sensors. So at some point we might have had like 100 sensors online. This was generating about 40 terabytes of time series a year. Okay. So I think we might have, you know, like a few hundred terabytes of data. These, and in another set of slides, I actually have the location of the sensors, and they were clustered around 2 areas, the Washington Square area, because those are NYU buildings that we actually had power in network, right? And also in Brooklyn because of the same reason, right? And we actually towards the okay. So one of the things that we actually initially we thought that maybe we could have a larger network of sensors for sound, but it was very costly. So what we actually did, and that's what that second, let's see here, we changed to this model towards the end. This is a different model. Instead of you trying to sense everything every time, this model here is anytime someone now complains, then they get their sensor. Okay. But actually, one of the reasons that you can do this now is because you already did the other sensing, you did the other training. Now you're able to recognize the sounds. Okay. There was labeling, there was all that stuff, right? So now you can apply this, but you couldn't do this. If you're starting up, you couldn't do this, you know. So yeah, so I mean, any one of these projects, there is a certain amount of complexity that I unfortunately probably failed, but yeah, but hopefully this clears up. Yeah. And yes.
Thank you for I have 2 questions. First, if we expand this kind of urban science researches to other cities, like Seoul, for example, what would be the challenges for expanding? This is first question. And secondly, for this process, we have to collect high resolution data set for city environment. And are there any legal issues for collecting that information? There are a lot of anonymous people.
That is a great thing. So for instance, let me answer the second one first because it's easy. Yes. So for instance, the sound, we had a very specific, like in the US, we have to do this thing called an IRB. It's to make sure that people are not going to be harmed by our research. So for instance, we had to make sure that the recording we were doing couldn't be used for reconstructing people's voices. Okay. So we had a protocol where we would throw away a piece of the data, and you know, so you always have to care about those things, right? You know, and there, like in some places, people have lots of more access to data. For instance, I remember I once gave a set of talks like this, like on urban in Russia, and I was amazed. Like in Moscow, they have all the data, they have everything. They like the illegal conversion problem would never be a problem in Russia because they actually know, like based on power consumption in an apartment, they know how many people are there. Okay, so I mean, then so some places you can do certain things that you cannot do in other places, right? So the challenges of applying this kind of technique. So one of the reasons that I think we need to develop, I go to the end here, is to this thing here. We need to develop like a suite of tools, okay? Is because a lot of these things, they are similar and they can, the basic core technology can be applied to different places, okay? But then you need kind of like plugins. So for instance, like you're gonna need to, maybe the surface materials that people use in Seoul are different than the ones in New York, okay? So you might need to fine tune those models differently. The other thing is for New York, a lot of the city data is actually already in databases, and what actually made New York kind of like a really nice example to where to like get data from. But even in New York, for instance, there is this thing called the Pluto dataset. What the Pluto dataset is effectively the businesses that are the lots that exist in the city and how they change over time. Okay, I imagine that data like that because, for instance, I'm from Brazil, and I learned that there is an equivalent version of that data for the city that I was born. Okay, in New York it's public. You can Google it and say like New York City Pluto data set, and then you can just download it, right? For my city in Brazil, it's not public for some reason. I don't know why, right? So I mean, all these things you're gonna need to figure out, right? But I would say that most of the technology that we are developing, not only us but a bunch of other people, is applicable anywhere, right? So road networks. I think people have. There's so many of these things that are very similar, and a few things that are very different. I think that so sidewalks in certain areas of the planet are very different than in others. So yes.
I have a question regarding how this data could be used. So you mentioned a lot of data such as taxi and the sidewalk data. And so I think those data and analyzing it is also important, but I think using the data is also an important task because there could be issues regarding accessibility to information. So I want to ask if there was any examples or the actual pieces that the data that you mentioned are used in New York or the government or.
Yeah, no. So the government has used the data in very different in a lot of different ways. So I would say that for instance the DOT used TaxiViz for analyzing traffic, right? One of the things that I try to we try to develop tools that are general enough that people can use, right? And use some of their use cases. You can actually, if you read our papers, there's going to be some very specific examples that in each one of these papers that we talked about. But personally, I have so long refrained from becoming an expert on that domain. What I mean by this is I'm never going to be, although I worked with the taxi data for like 10 years, okay, I'm never going to be a transportation expert, okay? So I have a colleague, Kan Osbe, he's the head of the C2 Smart Center. That's a national US center for transportation that is headquartered at NYU. I let Kan drive the transportation research, right? So I think that this is trying to understand enough that I understand what the problems are, but that I'm not the one driving it. It's like, because, you know, there's people that are experts in that. Does that help? Yes.
Wondering how long does it take for the government to actually go into the research? I mean, do you have an idea? Usually we publish a paper, but it's rarely the case that it's actually deployed.
That's a great question. So my experience has been that some things have been very immediate. But
Do you have a tip?
but other things, I've had experiences of even things that were very obvious and very easy to be deployed. And people decided not to, because they thought that the tool was going to be misunderstood. So there was actually, I have a particular example. I'm not gonna say what agency, because otherwise I would be, but when the experts look at it, they said, I don't want to make this available to the public because the public does not understand the context of these numbers. And this tool is useful for us, but not for the public, right? And originally we had developed it as a way to make the government more transparent, right? But their point was, and it's fair, is that transparency would actually be providing misleading information, in the sense that it was the real data, but we don't know how to interpret exactly that data. That's their point. And then they would get all this, let's say, all kinds of, look, working on these things, right? If I search my email here, I can show you, like, people send me messages like, my neighborhood is noisy, blah, 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 blah. Can you talk to me about it? Sorry. Oh, I read on the New York Times that there's this project. So it's very interesting, right? I mean, we are not government employees here. So. The NSF funding for it ended last year. So we are still developing sensors, but are different. We actually just had a paper published that these are, instead of trying to do sensors that you deploy, very cheap sensors you deploy everywhere, we are now doing these sensors that are a bit heavier, but that you do a local deployment. So what we are doing is we have these audio-visual sensors. And actually what we are doing is we've been recording some intersections because we are trying to understand how people navigate traffic, how people, as they walk, and you know, there's some technique. I'll be happy to send you the paper on that. But the Sonic project per se, it was funded for about 6 years by NSF, and then the funded ended. So if anyone wants to continue, let's say if the city wants, they can just, you know, deploy what was done, or get a contractor to build on the research. But all the building blocks exist.
As I found, the data collection website is still ongoing. Can you tell me what was the sensor resolution of the network?
The sound sensor? Oh no, I mean it was only about 80 to 100 sensors. 80 to 100 sensors throughout the city. Actually, if there's a paper called Life of a Sound Sensor, something, I don't remember the exact title. If you look on the Scholar, you're gonna find it. It actually has a picture of all the locations of the sensors at that particular day. So you can see the density and you can see their location. Yeah, sure. Yeah, the data, don't know if I'm we do have a copy of all the data. It's just that so the raw data, even with the IRB protocols, we feel that it's kind of sensitive just to make it available to everyone. So yeah. Cool. So I mean, it was wonderful talking here. I hope, I hope this was informative. Thank you so much. I really appreciate